Hello students, welcome to lecture number 5 on the topic relations. Today we will discuss total number of relations from set A to set B. Right? Let A and B be two non-empty finite set. Now finite set means this set has some finite number of elements. So let the cardinality of A is P and the cardinality of set B is Q. Then the Cartesian product of this A cross B consists of PQ ordered pairs, right? Therefore total number of subsets of A cross B is 2 to the power cardinality of A cross B, which is equals to PQ, right? As cardinality of A cross B is equal to cardinality of A times cardinality of B. So cardinality of A was P and the cardinality of B was Q, so cardinality of A cross B is PQ. So total number of subsets of A cross B is equals to 2 to the power cardinality of A cross B. Now since each subset of A cross B defines a relation from A to B, therefore total number of relations from set A to set B is 2 to the power PQ. This is very important, right? This, suppose we have a set, say A, this set contains A, B, C, and suppose we have another set B which contains two elements, right? Suppose we want to find the number of relations from set A to set B. We want to find the number of relations from set A to B. This will be equals to 2 to the power cardinality of A multiplied by cardinality of B. So here cardinality of A is what? A contains 3 elements, so the cardinality of A is 3. Similarly B contains 2 elements, so the cardinality of B is 2. So cardinality of A is 3 and cardinality of B is 2. So 2 to the power 6, which is equals to 64. So total number of relations from set A to B is 64, right? I hope this concept is clear to all of you. Now see over here, since phi is a subset of A cross B, here phi means the empty set, right? So phi is a relation from A to B, as from the definition that any subset of A cross B is a relation from set A to set B. So phi is a subset of A cross B, therefore phi is a relation from set A to B, and phi is called the empty relation, right? Here phi is called the empty relation. Similarly A cross B is a subset of A cross B, right? As A is a subset of A and B is also a subset of B, so A cross B is a subset of itself. We know this from set theory, right? And since A cross B is a subset of A cross B, therefore A cross B is a relation from A to B. This type of a relation is called universal relation, as you may see here, right? Next topic is the relation on a set A. Suppose A be a non-empty set, then then a relation from set A to itself. Set A to itself means R is from A to A only, right? That is A cross A is called a relation on a set A. Means the elements of A maps to elements of A itself. So if we want to find the total number of relations over here, this will be equal to 2 to the power cardinality of A cross A, right? This will be cardinality of A times cardinality of A, right? Suppose cardinality of A is say m, so this will be 2 to the power m into m, which is 2m square, right? So this is represented by this arrow diagram also. I hope this topic is clear to all of you. Now let us see some good questions as well. Suppose we have let A contains 1, 2, 3, 4, 5 and 6, right? We define a relation on set A, means R is from A to A by R equals to xy such that y equals to x plus 1, means R contains the ordered pair of the form x comma y such that second component is x plus 1, means second component is 1 less than the first component, right? We are asked to find out the domain, codomain and range, and we have to write R as a set of ordered pairs, and we need to depict this relation using an arrow diagram, right? So given A equals to 1, 2, 3, 4, 5, 6, A contains these elements. Now we want to find those ordered pair of the form xy where this condition is satisfied. We want to form a relation from set A to itself where this condition is satisfied. Now we put x equals to 1, we get y equals to x plus 1. This is the condition. We put x equals to 1 as this 1 belongs to set A, so y equals to 1 plus 1 equals to 2. This also belongs to set A, and this satisfies this condition as well, so 1 comma 2 belongs to R. Similarly, put x equals to 2, you get y equals to 3. Now this 2 also belongs to set A and 3 also belongs to set A, and this satisfies this condition, so 2, 3 belongs to R. Similarly, you can check for 3, 4 and 5, but when you put x equals to 6, see here, x equals to 6, this belongs to A, but 6 plus 1, 7, this does not belong to A, so this pair 6 comma 7 will not belong to R, right? Therefore R is this. This is your final answer. Now depict this by an arrow diagram. So R is a relation from set A to set A, right? So from here 1 maps to 2, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 6, but 6 cannot go to 7 as 7 is not present in set A, right? I hope this question is clear to all of you. Next, we need to find the domain and range of R. See, domain of R will be the set of first components 1, 2, 3, 4 and 5 by the definition also. Domain of R contains A such that AB belongs to R, means the first component, right? So first component is 1, 2, 3, 4, 5 and 6, which is set A itself, right? And the range of B contains range of R contains B such that AB, means this is the collection of all second components, right? So second components in R are 2, 3, 4, 5 and 6. 2, 3, 4, 5 and 6. This is again a subset of A, and the codomain of R is the set A itself, right? So here the domain was this and the codomain also was set A, right? I hope this question is clear to all of you. Similarly, we have discussed this question number 2 in our previous lecture. You can view this question on lecture 4, right? So next, question number 3, you can try this yourself. Now see question number 3. Determine the domain and range of the following relations. So first is R1. So R1 contains of those ordered pair of the form AB where the first components belongs to the natural number, and this is A is less than 5 and B equals to 4, means B is fixed and A varies. Now A belongs to natural number, and we know set of natural number starts from 1, 2, 3, 4, 5, 6 and so on, right? So A is less than 5 and A belongs to this set, means A is equal to 1, 2, 3 up to 4, right? This same statement is over here also. Yes, A belongs to 1, 2, 3 and 4 and B is fixed as 4. So we write the relation as 1, 4. 1 maps to 4, 2, 4, 3, 4 and 4, 4, right? So the domain of R1 is what? The set of all first components, that is 1, 2, 3 and 4, and the range of R1 is what? The set of all second components, which is the singleton set 4, right? Next, for S. Now S contains the ordered pair of the form AB such that B equals to mod of A minus 1, and A belongs to the set of integers and mod A is less than equals to 3. Okay. So first we have this as S, right? So B equals to mod A minus 1. This condition it satisfies, and A belongs to the set of integers. Integers are of the form 0, plus minus 1, plus minus 2, plus minus 3 and so on, and mod A is less than 3. What does this line means? This means that A lies from minus 3 to 3. If you have mod x less than 2, this will always imply that x lies between minus 2 and 2. Similarly, if you have, suppose, say B, mod B less than 5. So B lies from -5 to +5, right? This is the case over here also. Mod A less than equals to 3 means A lies from -3 to 3, right? And A belongs to the set of integers, so A will be from -3 to 3 and all those integers between -3 and 3. So -2, -1, 0, 1, 2, right? Now we have to check that which A satisfies this condition, right? So put A equals to -3 in this condition, then B equals to mod of -3 -1, which is equals to mod of -4 is 4 itself, and 4 lies in here, right? Similarly, put A equals to -2, B equals to 3. So we are getting R as the first pair was -3, 4, then we get a -2, 3, then we get a -1, 2, right? You put the values of A and get the values of B, right? So 1, -2, then 0, 1, then 1, 0, 2, 1, and 3, 2, right? See this here, this is our R, this thing. Now to find the domain of R is the set of all first components. So domain of R is -3, -2, -1, 0, 1, 2, 3, right? And the range of R is what? The set of all second components, 4, 3, 2, 1, 0 and 2 itself. 4, 3, 2, 1, 0, 1 and 2. Here 1 will be only once, okay, and 2 also. Yes. I hope this question is also clear to you. Comment down if you have any questions. Now see question number 4. Find the total number of relations from set A to set B where A is XYZ and B equals to AB. So given A equals to XYZ, then the cardinality of A equals to 3. We denote the cardinality by n of A, or like this. Both have the same meaning, right? So the cardinality of A is 3. Similarly, cardinality of B is 2, since B contains 2 elements only, A and B, right? So the total number of relations from A to B is equals to 2 to the power cardinality of A times cardinality of B, which is equals to a cardinality of A is 3. So 3 times 2 is 6. So answer is 2 to the power 6, right? Next, question number 5. Let R be a relation from set of a natural number to set of a natural number itself, and defined by R equals to AB such that A equals to B square. It satisfies this condition. So all those pairs which satisfies this condition will come in R, where AB belongs to natural number. Then which one of the following is true, right? So we have to check all the 4 options. So let us check the first option. Now A comma A, they are saying A comma A belongs to R for all A belongs to N, right? Suppose we take A equals to 2, then A comma A pair will be of the form 2 comma 2. Now can this belongs to R? No. Why? As it should satisfies this condition, means first component should be equal to the square of the second component. This first component should be square of this second component. So is 2 equals to 2 square? So no. So 2 comma 2 will not belong to R. So a comma a square can be in R, but a comma a cannot be in R, right? So option A is incorrect. We cancel this. Now check for option B. Check for option B. AB belongs to R means BA belongs to R. Is this true? Let us see over here. Now AB belongs to R means it satisfies this condition, A equals to B square, right? So A equals to B square. Now if BA belongs to R, then this implies that B will be equal to A square. First component should be the square of the second component, right? Now let us take one example. 4 comma 2 will belong to R, right? As 4 equals to 2 square. But 2 comma 4 will not belong to R, as 2 is not equals to 4 square. So this option is also wrong, right? Hence option B is also incorrect. So it is not necessary that if AB belongs to R, this implies BA belongs to R, right? This condition fails here, hence option B is also incorrect. Similarly, we check C over here. Now AB belongs to R and BC belongs to R. This implies AC belongs to R, right? Now we need to check this. Now see, since AB belongs to R, so this must satisfy this condition, A equals to B square, right? So A equals to B square, and BC belongs to R means B must satisfy this condition, so B equals to C square. Now see, B equals to C square, right? Now squaring both sides, C square square, right? So B square is C to the power 4, and from here we have A equals to B square, means combining these two we get A equals to C to the power 4. How? As A equals to B square equals to C to the power 4, so A equals to C to the power 4 means A equals to C square ka square. So A comma C square pair can belong to R, right? But A comma C will not belong to R. Hence option C is also incorrect, right? So option D is the only correct answer, right? Option C is incorrect, so none of the above. I hope all the questions are clear to you, and one homework question for you is this question number 6. You may try this and comment in the comment section, right? You need to find here the domain of R and the range of R. Thank you for watching my lecture. Thank you all.